Hey there, physics students. Welcome back to another in our rapid review series for honors physics. Hey, today we're going to talk about problem solving for drop problems, acceleration due to gravity, dropping things, throwing things up and down, maybe catching them, maybe not. So acceleration due to gravity, this is motion in the vertical direction, right? Because that's the way gravity works. We tend to teach this as 4 different kinds of problems called drop problems and up and down catch and whatever else. But really, if you think about it, they're all the same kind of calculations. They all use these same 4 equations that we know and love and have seen quite a bit, right? So as I approach these, I'll talk about how the different types relate to the different, how the different problem category types correspond to the equations that we already know. Okay, so the first category we call a drop problem. What's special about that is the initial velocity is 0, so I can just cross out anywhere I see initial velocity. I can cross that out. They don't count anymore. You could choose to rewrite these equations as v equals at and I'll be fancy here, delta y equals 1/2 at squared, etc. But you don't have to do that. You can just use the original equations. And just remember, when you use them, the initial velocity, when you drop something, is 0, because it's starting from rest. Okay? So that is a drop problem. Do I need to solve it? Probably not, but let's talk about the approach. If I drop a ball, here's a problem statement. If I drop a ball from some height, how far will it fall after a given time? And when it asks how far, what it's asking is a distance question. So we can go ahead and calculate displacement, right, y minus y0, and then we can take the magnitude of that, and that's the distance it falls. Okay, so let's go back to the problem statement here again. We understand the words. How far means distance. Delta y means y minus y0. And I will not solve this problem here in this presentation. I have decided, because this is a rapid review, that you've probably seen problems like this solved already, and I'm going to focus more on the thought process and what you should be thinking about as you approach these problems. I also make the point here that any origin is fine. So if you want to do a little experiment, this is a new problem that was not in the problem statement, just a little experiment. You can solve for the total time in air by assuming your origin is maybe at the drop height, or maybe your origin is at ground level, or maybe you could even think of some arbitrary, crazy origin right in the middle. You'll always get the correct answer as long as you stay consistent with your coordinate system when you solve the problem. Let's go on to the next category. We call it an up and down. I'm going to click through a lot of statements here that are already on the slide, but worth remembering. There's everything about the up-down problem is what you think it is. There's symmetry throughout all of the concepts of an up-down problem. So I'm throwing an object from point A. It's going to go up to point B, maximum height, and then fall back down to C. Let's take a look at that. Fun facts. The time up is the same as the time down. The total time, therefore, is going to be twice the time up. Also, twice the time down. The speed at point A is the same as the speed at point C. And if you're thinking about it, you'll realize, of course, the velocity will be opposite. The direction of the velocity vector at point A is opposite to the direction of the velocity vector at C. Everywhere in this image, gravity is acceleration, right? So if you see an A in the equation, you use g for that, negative 9.81 meters per second squared. One more comment about the top is it may not be obvious, but the acceleration at the top is g. also. So not only is the acceleration g on the way up and the acceleration g on the way down, but classic test question. What is g at the top? It's the same. Or what is the acceleration at the top, right? It's going to be g negative 9.8 meters per second squared. If I wanted to solve a problem here for an up-down problem, usually a good strategy is to choose either the trip up or the trip down. Because if you do that, let's say I want to look at the trip down, I would then look at my handy equations, and I would say, for the trip down, there is no initial velocity. Isn't that nice? I get to use that. I have to remember, though, if I do that, what the meaning of this t is, right? If I'm going to get rid of the initial velocity, I have to remember that this is the time for the trip down, t sub down. I strongly encourage you to use subscripts, down, up, or something else, entire trip or total or whatever, for your t's, because that is a very common mistake, to lose track of which part of the trip you're calculating. So use a subscript for your t, and you'll do well. Next is the up-down cliff category. I will not read all of these bullets. You can read them off the slide, but the important thing is you don't anymore have the symmetry between A and C, because the whole trip is asymmetrical. It's going to be moving faster at C than it is at A, for example. Okay? So I will not read this slide, but if you would like a review, you can check into this again. If you understand up and down, I think you will understand this quite easily. Now, I might have time at the end to solve this problem. If time permits, I will at least explain how this was approached and the different kinds of approaches you could do. But in order to be complete, I'd like to show you the fourth category of problems. We call them the throw down, and it's pretty straightforward. Think of a football spike or a volleyball spike. The initial velocity is straight down, so you're throwing something in a downward direction, thus it has a negative initial velocity, right? So velocity of -3 meters per second would be a legit kind of question to ask. That's the only thing that's special about a throw down problem. It's just you have to remember that velocity is negative if you're going down. Okay. I will next mention only briefly, if you're using different notation than I do, you might run into this slide. I'm not going to go into this slide in detail, but would suggest that if you're using the notation that's on this slide, that you remember position, or the D represents position, and the A represents G, which is gravity, and the A, B, and C in this slide are the quadratic coefficients. Importantly, the A in this slide is not acceleration, it's the quadratic coefficient, like ax squared plus bx plus c that you see in math class. Okay, and let's go now, we have a minute left here, let's go now to talking about how to solve the up-down cliff problem that was presented earlier. I will use a quad solver to calculate the roots of the quadratic equation. Often you're going to have to do this. In your class, you're probably allowed to use a calculator to solve quadratic equations, so you don't have to use the quadratic formula that you learned in algebra and do all those extra calculations. Okay, so for this problem, you can arbitrarily set up your coordinate system. I chose y equals 0 to be ground level. You might have chosen something else. And we're being asked to find the total time in air and the final velocity. I'd like to illustrate that your approach can vary. You might do the whole problem all at once. And if you do it, I'll leave this up on the screen. You can see that I solved the quadratic formula first with the appropriate coefficients, and I found the time in air. Then using that information, was able to find the final velocity. Notice that the quad solver creates two roots. You're familiar with this now. You pick the one that is obviously correct. In this case, it's the one that has the positive time. Here's another method. You can think about this as an up problem and then a drop problem. So I divided the picture into two pieces. I'll leave this up. I will not read everything I did here. You will probably agree with me that this turned out to be a little harder than my method 1. Worse was my method 3. Here, I thought about it in terms of an up-down problem and then a throw-down problem. You can see how splitting it up is totally legit. You can do this. I stumbled upon a lot of complicated math to do it. I'll leave that up, and you can read it if you want to see exactly how I solved it. My method 4 turned out to be the best. I just got V first. Instead of answering the questions in the order that they were asked, I just solved for V, and then after that, I looked for time. So if you look at my work here, you'll see that the finding V was pretty quick. It was only a couple lines of algebra, and then once I did that, finding T was also pretty quick. So big point here in green, for multi-part problems, it's okay to solve in any order. Just because the test question asks you to find first T and then V doesn't mean you can't do it in any order you want. If you have experience and practice, you might have good intuition as to what's the best way to approach these problems. But no matter what, if you're careful, it doesn't matter how you think about them and how you structure them. So long as you solve correctly, you'll always arrive at the right answer. That's all I have for today in solving up and down problems. We'll see you next time.